The production of forged steel bars commences with the arrival of raw materials, usually alloyed or carbon steel billets. These billets serve as the foundational building blocks for the entire process. The initial step in the manufacturing process is sawing, a crucial operation that transforms the steel billets into more manageable pieces. The sawn steel pieces are then heated in a furnace to a specific temperature. This process, known as heating, softens the steel and makes it more malleable for forging. The temperature is carefully controlled to achieve the desired metallurgical properties. Upsetting is a controlled deformation process that involves applying compressive forces to the steel, which results in an increase in its cross-sectional area while simultaneously reducing its length. This controlled compression serves a pivotal role in forging, as it imparts uniformity to the steel's shape and density. Consequently, the material's structural integrity, strength, and overall quality are greatly enhanced through this process. Setting down is a critical step in the forging process where the steel bar's diameter is systematically reduced. This transformation is achieved through a meticulously executed sequence involving dies and hammers. As the steel passes through these tools, it undergoes controlled deformation, gradually shaping it to the desired diameter. This step is instrumental in refining the dimensions of the bar, eliminating any surface irregularities, and ensuring a consistent diameter, thereby contributing to the bar's overall quality and structural integrity. Solid forging is a critical step in the manufacturing process. Here, the heated and shaped steel bar is further compressed and shaped using a series of dies and hammers. This process increases the bar's density and refines its grain structure, improving its mechanical properties. Cogging represents a pivotal hot forging stage aimed at further enhancing the steel's shape and structural characteristics. During this intensive process, the pre-forged steel bar undergoes multiple passes through a series of meticulously designed dies and hammers. With each successive pass, the steel's dimensions are meticulously adjusted, and its internal grain structure is refined. Cogging plays a vital role in achieving the precise dimensions and mechanical properties required for the final product. It imparts superior strength and uniformity by breaking down any remaining irregularities or inconsistencies. This repetitive refinement process is a testament to the meticulous craftsmanship involved in forging steel bars of exceptional quality and reliability. Scarfs, unwanted surface irregularities or imperfections, pose a risk to the forged steel's structural integrity. In the scarfing step, specialized tools or machinery are employed to meticulously eliminate these flaws. This process ensures that the bar's surface is rendered smooth and devoid of any defects, guaranteeing the final product's strength and reliability. To optimize the forging process, coal or other lubricants are strategically applied. This measure serves to mitigate friction between the steel and the forging dies, making the deformation smoother and more controlled. Additionally, these lubricants aid in maintaining the steel's elevated temperature and prevent undesirable adhesion to the dies, ensuring the efficiency and integrity of the forging process. Hollow forging involves creating a hollow section within the steel bar. This process is used when the final product requires a hollow interior, such as in the case of hollow shafts or tubes. Expanding is the reverse of upsetting, where the steel is stretched to increase its length while reducing its diameter. This step is essential for achieving the desired dimensions and shape of the forged bar. The straw boss is a portion of the steel bar that remains unprocessed during forging to serve as a reference point for subsequent operations. It helps ensure uniformity and consistency in the final product. Tap forging involves shaping one or both ends of the steel bar to meet specific requirements, such as threaded or tapered sections. This step adds functionality to the forged bar. Following the forging process, steel bars may exhibit minor deformations or bends. To rectify these imperfections and meet stringent dimensional tolerances, straightening machines are employed. These machines meticulously restore the bars to a perfectly straight condition, ensuring uniformity and structural integrity. Subsequently, the forged steel bars are cut to the required lengths with precision cutting equipment. This step guarantees that each bar conforms to the exact specifications, making them ready for further processing or incorporation into larger components, contributing to the precision and reliability of the final products. In certain applications, where exacting dimensions and pristine surface finishes are paramount, machining becomes an essential step in the manufacturing process of forged steel bars. Machining is a precision operation that employs cutting tools and equipment to meticulously shape and refine the bars to meet specific specifications. During machining, specialized tools, lathes, milling machines, and grinders are utilized to remove excess material, create threaded sections, or achieve fine surface finishes. This level of precision ensures that the forged steel bars meet the most stringent dimensional and surface quality requirements, making them suitable for critical applications in industries such as aerospace, automotive, and machinery manufacturing. Machining adds the final touches, enhancing the bar's functionality and performance. Heat treatment is a critical step in enhancing the mechanical properties of forged steel bars. It involves heating the bars to specific temperatures and then cooling them at controlled rates. Normalizing is a specific heat treatment process that helps refine the grain structure and relieve internal stresses in the steel. Tempering is a critical post-forging heat treatment process that significantly influences the mechanical properties of forged steel bars. While the initial forging and heat treatment processes enhance the steel's strength, they can also make it overly brittle. Tempering serves as a balancing act, imparting essential properties such as toughness and ductility without compromising strength. The tempering process begins by reheating the forged steel bars to a temperature lower than that used during normalizing. The exact temperature is meticulously controlled to achieve the desired balance of properties. The bars are then held at this temperature for a predetermined time, allowing for the structural transformation of the steel. Crucially, tempering involves a controlled cooling phase, which is typically slow and gradual. This gradual cooling minimizes the risk of thermal shock and cracking, ensuring that the steel retains its newly acquired properties. The result is a forged steel bar with improved toughness, resistance to impact, and ductility, making it better suited for applications where dynamic loading or stress is a concern. Run-out measurement and inspection quality control is paramount in the manufacturing of forged steel bars. Run-out measurements and inspections are conducted to ensure that the bars meet the specified tolerances and quality standards. Dimensional accuracy is crucial in many applications. Dimension measurements are performed to ensure the bars meet the required specifications. Magnetic particle testing is also conducted to detect surface and near-surface defects that may have occurred during the forging process. Ultrasonic testing is employed to detect internal defects and irregularities within the forged steel bars. Additionally, material testing is conducted to verify the steel's composition and mechanical properties. Tensile testing assesses the strength and ductility of the forged steel bars by subjecting them to controlled tensile forces. Impact testing evaluates the material's ability to withstand sudden loads or shocks. To ensure the forged steel bars remain in pristine condition during transportation and storage, rust prevention measures are implemented. This often involves applying a protective coating. Finally, the finished bars are packaged and shipped to customers or distribution centers. The steel is heated to its melting point using an oxy-fuel torch, and then a stream of oxygen is directed onto the heated metal, causing it to rapidly oxidize and melt away. After flame cutting, the steel components may have rough edges or imperfections. Grinding is performed to smooth out these rough edges and achieve the required surface finish. Grinding also helps to remove any residual material and prepare the steel for the subsequent welding. Welding is a vital step in structural steel fabrication. It involves joining two or more steel components together using heat and pressure. Welding ensures the structural integrity of the fabricated components. It requires expertise in understanding different welding processes, filler materials, and weld joints to ensure proper fusion, strength, and adherence to industry standards and specifications. Welding is essential for creating metal frameworks, bridges, buildings, and other complex structures. Once the welding is complete, destructive tests are conducted to evaluate the strength and quality of the welded joints. In addition to destructive testing, non-destructive tests are performed to detect any potential defects or flaws in the fabricated steel components without causing damage. Non-destructive testing techniques include ultrasonic testing, magnetic particle inspection, and visual inspection. Before proceeding to the final stages of fabrication, a thorough dimension check is conducted to verify that the steel components meet the specified dimensional requirements. To prepare the steel components for surface finishing and painting, sandblasting is performed. This process involves propelling fine abrasive particles at high speed onto the surface of the steel. Sandblasting removes rust, mill scale, and any other contaminants, leaving the steel clean and ready for the application of protective coatings. Erection is the final stage in structural steel fabrication, where the fabricated components are assembled and installed at the construction site. Workers utilize specialized equipment, cranes, rigging, and bolting tools to lift, position, and secure the steel components into place. The accuracy and precision of the erection process are vital to ensure the structural integrity and safety of the final construction.
The process begins with the preparation of end plates, which are essential components for connecting and supporting the piles during construction. High-precision cutting machines are used to cut concrete into the desired lengths, with strict adherence to design specifications. Pile ends are shaped into buttons using specialized machines, ensuring stability during installation. Steel cages are fabricated to reinforce the concrete piles, enhancing their load-bearing capacity and structural integrity. Molds are automatically lubricated to facilitate easy removal of the cured piles, preventing sticking and ensuring uniform quality. The steel cage is precisely positioned inside the mold, ensuring proper reinforcement throughout the pile's length. High-strength concrete is poured into the mold, encasing the steel cage and forming the core structure of the pile. Pre-stressing wires are tensioned to induce compressive forces in the concrete, improving the pile's resistance to bending and shear. Concrete mix is prepared with precision through automated batching to maintain material consistency. Modern concrete pumping technology efficiently fills the molds, reducing the risk of air voids and ensuring uniform density. Rotating the filled molds evenly distributes the concrete mix and maintains uniform density. Controlled steam curing accelerates concrete strength development and enhances durability. Automated processes and vacuum lifters carefully remove the cured piles from the molds. Each pile is labeled with critical information, including specifications and batch details. Random samples undergo compressive strength testing to ensure they meet design requirements.
The primary raw materials used in ductile iron pipe manufacturing are iron ore, scrap iron, and various alloying elements such as magnesium and cerium. These materials are carefully selected to ensure the desired properties of ductile iron, including its high tensile strength, ductility, and resistance to corrosion. The iron ore is typically obtained from mines and undergoes beneficiation processes to remove impurities. The next step is the melting and smelting of the raw materials. This is typically done in a blast furnace, where iron ore is melted at high temperatures. Alloying elements are added to the molten iron to transform it into ductile iron. The addition of magnesium and cerium promotes the formation of graphite nodules within the iron matrix, giving ductile iron its unique properties. The molten metal is carefully monitored to ensure the desired chemical composition is achieved. Once the molten metal reaches the correct composition, it is poured into molds to create the basic shape of the ductile iron pipes. The molds are typically made of sand, and they are designed to create a pipe with the desired dimensions. The casting process can be done using various methods, such as centrifugal casting or static casting. Centrifugal casting is often preferred for its ability to produce pipes with consistent wall thickness and strength. After casting, the pipes are subjected to an annealing process. Annealing involves heating the pipes to a specific temperature and then slowly cooling them. This process relieves internal stresses in the ductile iron, making it more ductile and less prone to cracking. Annealing also helps to refine the microstructure of the material, further improving its mechanical properties. To achieve precise dimensions and smooth surfaces, the ductile iron pipes undergo machining and finishing processes. This includes cutting the pipes to the required length, boring the interior to ensure a uniform diameter, and threading or grooving for connection purposes. Machining is a critical step to ensure the pipes meet the specified tolerances and standards. To protect the ductile iron pipes from corrosion and extend their lifespan, they are often coated with an external layer of asphaltic paint or a fusion-bonded epoxy coating. This coating acts as a barrier between the pipe's surface and the surrounding environment, preventing the formation of rust and corrosion. Quality control is a fundamental aspect of ductile iron pipe manufacturing. Pipes undergo rigorous testing to ensure they meet industry standards and specifications. Common tests include hydrostatic pressure testing to assess the pipe's strength and leak resistance, dimensional inspections to verify size and shape, and various mechanical tests to assess material properties. Once the pipes pass all quality control tests, they are packaged and prepared for distribution. Packaging methods may vary depending on the size and quantity of pipes being shipped. Pipes are often bundled together and protected with additional coatings to prevent damage during transport. The final stage in the ductile iron pipe manufacturing process is installation. Ductile iron pipes are widely used in water distribution and sewage systems, and they are laid underground or in trenches. The installation process involves connecting pipes using various fittings and joints, and it is critical to ensuring a reliable and efficient water or wastewater system.
The process begins with the arrival of large steel blocks. These blocks are heavy, each weighing as much as a small truck. They are the starting point for creating durable railway tracks. The steel blocks are placed on rollers and transported to a massive furnace. These rollers enable the blocks to move efficiently towards their destination. The blocks are heading to the furnace, a critical stage in the production process. Inside the furnace, the steel blocks are subjected to intense heat, reaching temperatures of up to 1,200 degrees Celsius. This high heat is necessary to make the steel malleable and ready for shaping. When the blocks glow red-hot, they are prepared for the next step. Upon exiting the furnace, the red-hot steel blocks may have black spots on them. These imperfections are removed using a water jet. The result is a clean, red-hot steel block ready for further processing. The steel block is flipped over and undergoes a rolling process. Water is used to cool the rollers to prevent overheating. The rolling process serves to elongate and flatten the steel block. This is achieved through a series of passes through the rollers, gradually making the block longer and thinner. Once the steel block reaches a certain length, it needs to be shaped into the proper rail profile. Additional water is used to cool the rolling rollers as the steel block is guided through them. During this process, the rail not only becomes longer, but also acquires a distinctive notch at the top. With each pass through the rollers, the notch at the top of the rail widens until it eventually takes on the shape of a T. This unique profile is vital for the stability and functionality of railway tracks. After the necessary passes through the rollers, the hot steel block is pushed onto another set of rollers with grippers. These rollers facilitate cooling as the steel block is transported among other stacker blocks. This cooling process helps the steel block solidify into a railway track. Although the rail has taken shape, it is not yet ready for use. Railway tracks must be perfectly straight. To achieve this, the rails are subjected to a straightening process. The rail is flipped over and run through heavy wheels that press down and lift it, straightening it both vertically and horizontally. The rail continues to be straightened until it reaches a state of perfection. At this stage, the rail is both straight and stable, ready to support the weight of trains and trams. The end result of this intricate production process is a railway track that is strong, straight, and capable of withstanding the heavy loads and continuous use of the railway system. The rails have a unique profile, with a thick top for the wheels to ride on and a flat, wide bottom for stability and attachment to the ties with clamps.
Raw materials preparation. The first step in hollow core production begins with raw material preparation. High-quality aggregates, cement, water, and additives are carefully selected and mixed to create a concrete mix with specific properties. The exact composition can be adjusted to meet the requirements of the project, ensuring the slabs will possess the desired strength and durability. Pre-stressing wire installation and tensioning. Once the concrete mix is ready, steel pre-stressing wires are installed. These wires are strategically positioned within the slab to provide it with additional tensile strength. Pre-stressing involves applying tension to these wires, which helps counteract the tensile forces that concrete alone cannot withstand effectively. This step is crucial for ensuring the structural integrity of the hollow core slabs. Casting and curing. The prepared concrete mix is then poured into a casting bed or formwork, which defines the shape and dimensions of the hollow core slabs. Vibrators are used to remove air bubbles and ensure even distribution of the concrete mix. After casting, the slabs are left to cure. Curing is a critical process that allows the concrete to gain strength gradually while maintaining the right moisture levels. It usually takes place in a controlled environment to achieve optimal results. Cutting. Once the slabs have sufficiently cured, they are cut into individual units. Precision is crucial during this step to ensure that the hollow core slabs meet the specified dimensions and quality standards. Advanced cutting machines are employed to achieve accurate results. Transfer to stock. After cutting, the hollow core slabs are carefully transported to a designated stock area. These slabs are typically stacked horizontally or vertically to prevent any damage during storage. The stock area should be well organized, and slabs are labeled for easy identification based on size, thickness, and other relevant specifications. The manufacturing process begins with the removal of the previously used molds or shuttering from the concrete elements. This step is typically done manually by skilled workers who carefully dismantle the molds, ensuring that the precast components are not damaged during the process. After the molds are removed, they undergo thorough cleaning to remove any concrete residue or debris. Once cleaned, a release agent is applied to the mold surfaces. The release agent prevents the concrete from adhering to the molds during the casting process, making it easier to extract the finished components later. Pallets that will be used to support the concrete elements during curing and transportation are cleaned using a specialized pallet cleaning device. This ensures that the pallets are free from contaminants and debris that could affect the quality of the precast components. In modern precast manufacturing facilities, automated plotting machines are used to create precise layouts and designs on the pallets. This step helps reduce human errors and ensures high precision in the placement of reinforcement and other elements within the concrete components. Side shifters are used to accurately position the reinforcement and other components on the pallet according to the plotted design. This technology enables efficient placement and minimizes the risk of errors. In some cases, additional shuttering may be required to define the boundaries of the precast elements. Workers manually add these shuttering elements to the pallet to create the desired shape and form for the concrete components. Reinforcement, such as steel bars or mesh, is placed on the pallet according to the design specifications. This reinforcement adds strength and structural integrity to the precast elements, ensuring they can withstand the intended loads and stresses. A concrete spreader is used to evenly distribute the fresh concrete mixture onto the pallet. This step requires precision to ensure that the concrete fills all the voids and spaces within the mold. To achieve the desired density and strength, compacting equipment is employed. Vibrators or other compacting tools are used to eliminate air voids and ensure proper consolidation of the concrete mix. Once the concrete is cast and compacted, the pallets with the precast elements are stacked and transferred to a curing chamber. Controlled curing conditions, including temperature and humidity, are maintained to facilitate proper concrete hydration and strength development. In some cases, the precast elements may need to be rotated or turned within the curing chamber to ensure uniform curing and prevent deformation. After the curing period is complete, tilting equipment is used to gently and safely demold the precast elements from the pallets. This step requires precision and care to avoid damaging the finished components. Steel bars are essential components in various industries, including construction, manufacturing, and infrastructure development. The production of high-quality steel bars involves a series of intricate processes that transform raw materials into finished products that meet stringent quality and performance standards. The reversible duo roughing stage marks the inception of the steel bar manufacturing process. In this initial phase, large steel billets, commonly in rectangular or square forms, undergo a critical transformation. These raw billets are meticulously heated to a precisely controlled temperature, rendering them more pliable and suitable for shaping. At the heart of this stage lies the reversible duo mill, a key apparatus comprising two powerful rollers. These rollers exert immense pressure on the billet, simultaneously reducing its cross-sectional area and increasing its overall length. This dual action serves two vital purposes. First, it refines the billet's shape, and second, it elongates it. This fundamental reshaping and elongation process is instrumental in enhancing the billet's workability, setting the stage for subsequent manufacturing steps. After the roughing stage, the elongated billets are cut into manageable lengths. Billet oxycutting is a precision process that involves the use of an oxygen-fueled torch to sever the billets into individual pieces of desired length. This step ensures uniformity in the steel bar's length and allows for better control over the manufacturing process. Once cut, the billet sections move to the cooling pit. In the cooling pit, the billets are placed on racks and allowed to cool gradually. This controlled cooling process prevents the formation of internal stresses and ensures the steel maintains its structural integrity. The cooling pit also aids in reducing the overall temperature of the billets to a level suitable for further processing. After cooling, the billets are transported to the pusher furnace. The pusher furnace is a high-temperature chamber where the billets undergo a reheating process. This is a critical step as it softens the steel and prepares it for the subsequent rolling operations. The furnace operates at precise temperature settings to ensure uniform heating throughout the billets. Once the billets reach the desired temperature, they exit the pusher furnace and enter the reversible duo terminator mill. This mill, similar to the roughing mill but with different settings, further reduces the billet's cross-sectional area and elongates them. This process refines the shape and size of the steel bars while maintaining consistent temperature and properties. Following the reversible duo terminator, the elongated steel bars proceed to the next critical stage, where they are tailored to meet precise specifications. Using a precision cutting saw, these bars are meticulously sliced into specific lengths. This step is pivotal in achieving the desired dimensions and ensuring uniformity across the finished products. The cutting saw operates with exacting precision, delivering clean and accurate cuts that align with the customer's specified requirements. This level of precision is vital in ensuring that each steel bar conforms to the exact measurements needed for its intended application, maintaining the highest standards of quality and consistency in the final product. In the culmination of the steel bar manufacturing process, the critical step of bar straightening ensures the bar's conformity to stringent quality standards. The bar straightener is a sophisticated machine comprised of a series of precision rollers and guides. Its primary purpose is to rectify any bends or deformations present in the steel bars, thus guaranteeing the required straightness. Beyond correcting structural irregularities, the bar straightener also enhances the bar's surface finish. This refinement ensures that the bars possess a smooth, uniform exterior, rendering them suitable for a diverse array of applications across industries. Ultimately, bar straightening plays a pivotal role in delivering steel bars that meet the highest standards of quality and performance. Lean management and production principles. The process begins with lean management and production principles. This involves minimizing waste, optimizing resources, and streamlining workflows to eliminate inefficiencies. This approach ensures that every step in the manufacturing process adds value. Highest raw material quality. Large bevel gears require the highest quality raw materials. Manufacturers adhere to defined standards, selecting materials that offer exceptional durability and resistance to wear and tear. The quality of the raw material is paramount to the longevity and performance of the final product. Fully automatic tooling setup. Automation plays a crucial role in large bevel gear manufacturing. The Chemo's calculation system is employed to fully automate tooling setup. This precision technology ensures that tools are positioned accurately, reducing the margin of error and enhancing production efficiency. Integrated manufacturing with closed-loop concept. Integration is key to maintaining consistency and quality throughout the manufacturing process. Manufacturers employ a reliable closed-loop concept where data from various stages of production is constantly monitored and adjusted in real time. This ensures that deviations from desired specifications are corrected promptly. Heat treatment facility. Large bevel gears undergo heat treatment to enhance their mechanical properties. Manufacturing facilities are equipped with state-of-the-art heat treatment facilities with a substantial monthly capacity of up to 140 tons. Controlled heating and cooling processes are employed to achieve the desired material characteristics. Physical contact pattern evaluation and documentation. Ensuring that the bevel gears have the correct contact patterns is critical for their performance and longevity. Advanced equipment is used to evaluate the physical contact patterns between gear teeth. This data is meticulously documented for quality control and future reference. Grind burn detection. For ground bevel gears, grind burn detection is an essential step. Specialized technology is used to identify any signs of thermal damage that may occur during the grinding process. Detected issues are addressed promptly to maintain product integrity. Quality assurance. Quality assurance is given the highest priority throughout the manufacturing process. Rigorous inspections, testing, and quality control measures are in place at every stage to ensure that the final product meets or exceeds industry standards and customer expectations. Optimized dispatch handling. Once the large bevel gears are manufactured and quality tested, skilled specialists handle dispatch optimization. This includes packaging, documentation, and logistics to ensure that the products reach their intended destinations safely and on time.